So on this other interesting question, we have a boom. Again, they have used the word uniform, a uniform boom. And we see that when something is uniform, we expect the whole weight to appear on the center of gravity. And we've been given its length. But then what they have talked about, hinged, meaning it's free to rotate. Whenever something is hinged, it's free to rotate. All right. So forces can easily influence it in terms of rotation, but it's fixed at one point whereby it can't move translationally. You can't translate it, but you can rotate it. All right. It's hinged to the ground. All right. But on top, on the other side, as you see on the diagram, a 50 Newton weight is attached to it. At the same point, it is tied to a cord, as shown below. We'll show it in the diagram. So the boom makes an angle of 30 degrees with respect to the ground. Calculate the whatnots. So I hope you're able to see. All right. So this is a boom. This whole thing is a boom. Like that. This is a boom. And it is hinged to the ground. So it is hinged here. It's free to rotate, but it is hinged. So it can either swing this way or swing that way, but it is fixed at this point. All right. And then there's a cord which is tied to it. On this point, there's a cord which is tied to it. And then there's a weight which is hanging on that point of intersection between the cord and the boom. There's another weight which is hanging 50 newtons. So this is what we have in our data. We have the boom, the weight. We have the mass, I mean the other weight here, the other weight, which is equals to this 50 Newton. The length of the boom is 7 meters, the angle 30 meters. Tension, which it makes in the cord, has been drawn like that. This is the tension it will make in the cord, like that. And then the force in the boom is this. What force will be exerted in the boom? Because here there's a mass, there's a weight which is hanged on it. So obviously there'll be some compression of force which will be felt in the boom. So this is the force in the boom. And the force R is the resultant force here. All right. The resultant force. This would be FR. Hope I could have drawn it, written it properly, but hopefully when I'll be sending a much neater diagram. But we'll have also the force which the boom exerts on the hinge. It will be in that direction. We are calling it FR. So we expect that on the boom, there will be a force in the x-axis. There will be a force in the x-axis, and there will be also a force in the y-axis, which is the normal. All right. There will be a force in the y-axis and the force in the x-axis. So let's see how we can compute the unknowns, what we don't know. The force, the reaction force, the force in the boom, the tension in the cord, with this information that we have been given. So a strategy that we are going to use sometimes it's not always clear where to start from. They're asking us find the tension in the cord, the force in the boom, the force exerted on the hinge. So sometimes it's not always clear where to start from. It is okay, actually, by the way, if you know that part 3 is much easier for you to solve, you can start even with part 3 and then go to part 2 and then go to part 1. You can, the way they have arranged them, part 1, part 2, part 3, is not always that you can start with you should start in this order. No, you can choose an order for yourself depending on which question is easier for you to solve. So for example, in this case, if you don't know which one is easier for you to solve, you can, since you know that it's a question on static equilibrium, you know that in any case, static equilibrium, I need 3 equations. I need 3 equations to be able to make sure that I resolve, or I make sure to determine its equilibrium, I need 3 equations. So you can start. You can start by your equation in the y-axis. You look at the forces that you have in the y-axis. Forces in the y-axis, we have the weight, which is hanging here, 50 newtons, and the weight of the boom, and the normal force, which is exerted on the hinge in the y-axis, in the y direction. All right. So these are the 3 forces that we have in the y-axis. So how do we find them? We know the weight of the boom. We know the other weight. These 2 weights are in the negative axis, y-axis, but the normal is acting upward. We can easily compute the normal and call it equation 1. We go in the x-axis. In the x-axis, in fact, in the x-axis, in this case, we don't have friction. We just, because this is hinged here. When something is hinged, there is no friction. So, but we have it positioned in this case, meaning in the x-axis, it is being restricted. There is a force in the x-axis. So it has, when the boom exerts a force on this hinge, there will be a force component in the x-axis. So we have this Fx, and we have our tension in the cord. These are our 2 forces in the x-axis. We don't know the force in the x-axis and the tension, we don't know it. We can compute, we can just leave it there as our equation 2. So we know our force in the x-axis, Fx is in the positive and the tension is in the negative. When we solve it, we can equate Fx to Fc. Now, let's see if we can compute torque. Summation of all torque is equal to 0. So taking counterclockwise rotation to be positive. Always taking counterclockwise rotation to be positive. And now here we are even taking the pivot to be the ground, or should I say the hinge, where the hinge is. Yeah, don't mind my handwriting on using a mouse, it's hard. So we are taking the point on the ground or the hinge to be our pivot, meaning we can pick this point to be our pivot. Mind you, we can even pick that point to be our pivot. Our pivot is just a point of reference where we want to compute our torque on. It's not always that the ground or the hinge should always be the pivot. You can pick any point, but it seems a bit convenient to pick this point to be our pivot. If we pick this point to be a pivot, meaning the few forces here will not consider them, we'll consider the forces on top there. Okay, so we know our tension in the cord will cause a positive rotation. All right, so looking at the direction here, it is going to cause that positive rotation. It's going to it's going to be counterclockwise, like that. So it's going to cause a rotation in that direction. And again, which one is our perpendicular distance? Our perpendicular distance is this distance, all the way to the hinge, this distance. All right. This will be our perpendicular distance when we talk about the tension. All right. This is the distance that makes 90 degrees with the force and the hinge. So again, our weight, our perpendicular distance will be that distance. All right. And we also have that other force here. Even it will be taking place in our computation for the torque. So we can extend it like that and then say this will be our perpendicular distance, like that. All right, D, and also we have D there. So let's see how we can now implement this in the equations. Now, in the equations, we are saying that we have been given the length of this ladder and we have also been given the angle. All right, so in this case, to compute the perpendicular distance, the height here. Oops. Oh yeah. Sorry about that. The pen just wrote something on its own, but I can easily remove them. Yeah. But the idea is to compute the distance from there to the ground or to the hinge. It's the same as the distance from there to the hinge, which is actually the opposite. So given the hypotenuse and the angle to find the opposite, we can easily use the sine function. No wonder I'm using the sine function with the distance. For the weight, I have this distance here. When I extend the weight, I have this distance here. And then this distance is actually half of the adjacent, because the adjacent, since this one appears on the midway, it will be half of the adjacent. All right. And half of the adjacent, we use the cosine function if you are given the angle and the hypotenuse. So the weight of the boom is at the perpendicular distance of 1/2 L cos theta. All right, the weight of the boom, this weight of the boom. But this other weight, which is here, hanging on the other side here, it will be the whole adjacent, because when you put it down, the adjacent will be actually the weight, the perpendicular distance. No wonder we have it here. We have the angle, we know the hypotenuse, which is the L, the length of the ladder. We can easily compute this. And then we realize that the only thing that we don't know is our tension. in the code here, we can solve for tension in the code like this. Simple as that. All right. And the tension in the code, we can even indicate now that our question 1, we have actually found our tension in the code. Then this can even give us now some muscles to say, okay, we have found question 1. Let's see if we can find question 2. Question 2 is saying the force in the boom. Where is our force in the boom? It's here. It's this force that is being exerted right in the boom. All right, the boom. It's being exerted by the tension in the cord and this weight here. So right here, as the boom feels some compression force, there'll be this force which we are calling FB. Now, how we can compute the force in the boom here? We know the component in the x-axis and we know the component in the y-axis. So we can use the magnitude of this component and that component to be able to find our force FB. And this is how we get to find it. All right, our FB will be our component in the x-axis squared, component in the y-axis squared. Now our component in the x-axis is the tension in the cord. Our component in the y-axis is that other weight which is hanging, and then replacing it with the actual values, squaring and doing the square roots, we find our FB to be 260.78, 264.78 newtons. All right. So you should be able to confirm these values. Go out and do the punching of the calculator on your own. Maybe I made a mistake or whatnot. But the idea is this is how to go about solving such a question. Are we following?
Yes, sir.
Oh, it seems Precious has disappeared. But anyway, I'm recording, so I'll send this document, this recording, even on WhatsApp. So hopefully people will be able to watch it there. So, yeah, we have found the force exerted on the hinge, the force in the boom. We can also find the force exerted on the hinge. On the hinge part, on the hinge, we know that we had found the normal force here, the force in the y-axis. What about the force in the x-axis? Because for us to know the force exerted in the hinge, on the hinge, which is the resultant, we need to know the x component and the y component. If we know the y component and the x component, it will be easy for us to find the force on the hinge. So let's try and see if we can find the x component. We found the y component, we already found it, which was this normal. It's normal force, we found it. So the y component here, we found it. Let's see if we can find the x component. Then when we find the x component and the y component, we can compute the resultant of the two. So how we go about it is like this. Remember that in equation 1, we can use it to find Fx, the x component of the force on the hinge. Because we know the tension in the cord, we said equation 1 that Fx is equal to the tension on the cord in the cord. That's what we said. Because these are the only forces which we have in the x-axis. Fx is pointing in that direction, and the cord is pointing in that direction. So we say that we can use these forces, and then this will even help us to find our force in the x-axis as being equal to the tension in the cord. So the same force that the same value that we found for the tension in the code will be the same value that we use here. Remember, I'm using the one which before I even rounded off. This is the one I'm using before I rounded off. Remember that we found this, and then when we rounded it off, we came to this. So don't use the one which you rounded off. Use the one that you have not yet rounded off, because you have not yet found your final answer. Your final answer should be the final rounding off to 2 decimal places. So if you have not yet found your final answer, you should use the one which is still having 4 decimal places. So we know the component of the force in the x-axis. We know the one in the y-axis, which we found here, the normal. It will be very easy now to compute the resultant, or the force on the hinge, by just computing the force in the x-axis and the force in the y-axis. And then on the force in the x-axis, we know is this fx, and the force in the y-axis is this normal. And then replacing the actual values, squaring and finding the square root, we find our FR to be that. So this brings us to the conclusion on static equilibrium. Hopefully next time we can do other topics, start another topic, hopefully on Tuesday. So are we okay? Any questions? Any concerns on this, on what we've learned?
That's fine.
You are okay?
Yeah.
Okay. Then I'm sure you do well to solve this homework. It's from the tutorial sheet. So
I saw just this night.
sorry.
I solved the question during the night. I'm saying I've already solved.
You have already solved this question, which is on the ladder in the tutorial sheet.
Yes.
Okay,
yes.
You can do well to send me so that I see the solutions. Yeah.
There's one in the same tutorial sheet which I think I would like to ask you the answer, the way they wrote it. They wrote 5V. They wrote, I don't know whether it's a mistake from there. They wrote 5V, like 5V, I mean 353, 353. Meanwhile, myself, 353.6.
Oh, you found 353.6.
Yeah, and then there they wrote 35V36.
Oh, okay.
That's the other question.
And
then if it so the same value to find the other one, now the next question it was giving another answer. When I use the one I used myself, the one I found, it was again giving me the other. So I was like, I may be wrong here. Maybe I contaminate the surface.
Okay. Okay. You show me the solutions and then I'll check through. Awesome. So have a good day, Mr. Gilbert.
All right. So is it fine? I can send just now?
Yes, you can send. You can send.
All right. Let me just send now. Let me just take the pictures.
Okay.